So we are going to discuss the different terrain types. So because each terrain has the different turbulence level that affects the bound layer height and other properties. So we have the flat terrain, urban terrain, forest, mountain, desert, then coastal, water, ice terrain, agricultural and volcanic terrain. So if you take the flat terrain, which has almost smooth surfaces, so very less turbulence. And if you take the urban, which has the low rise and high rise buildings, so this has the very complex flow pattern and high turbulence level. And the forest, so due to the dense vegetation, so here also the surface roughness is increasing due to the vegetation, so we have the increased turbulence here. And the next mountain, if you see here also there will be lot of peaks, ridges, valleys, etc. and all. So similar to the urban terrain, this also has the lot of turbulence. Additionally, there are a lot of flow separation in these sharp edges. Okay. So due to the sharp edges, ridges, etc. and all, there are a lot of flow separation. Additionally, it was found on the mountain. Then if you take a desert region, so it allows the other than the turbulence, etc. and all, there are a lot of convective turbulence. That is two types of turbulence. One is the mechanical turbulence, another one is the convective turbulence. Mechanical turbulence is whenever there is a flow over the object like trees, mountains, etc. and all, it is called mechanical turbulence. Then convective turbulence means due to the heat transfer. For example, in that surface, it is very hot, so the air particles, air parcel is rising, and it is mixing with the layer next to it. Okay, when it is rising, so that way it is causing the convective turbulence. As the surface temperature is very hot, there is a lot of convective turbulence also added in the desert region. Then coastal terrain like seashore, if you take, already discussed, there will be a sea breeze during the daytime and land breeze during the night time, which will affect the flow property inside this coastal region. Then water in the center portion, if you take ocean, sea and all, it is almost smooth surface and very less turbulence, and the bound layer thickness also very less here, very shallow bound layer. And next one is the ice terrain. This also almost a smooth surface with a very shallow bound layer, because the air becomes very cold and denser, so it will be very shallow bound layer formation will happen here. Then agricultural crops, if you take, it will create the moderate turbulence. Then this volcanic terrain, if you see, again this is also like a desert, there will be a hot lava in the surface, so this also has the convective turbulence other than the other mechanical turbulence. So these are all the different terrains. So other than that, there is a plateau, valley, canyon, etc. and all. Plateau already discussed, where we have the katabatic wind and anabatic wind, and valley, etc. we have the again valley breeze, mountain breeze. So these things are already discussed. So these are all the different terrain types. So next we have the atmospheric boundary layer. So atmospheric boundary layer means, so within the troposphere, this bottom portion is the atmospheric boundary layer, and the height varies from 2 to 3 kilometer to 0.2 to 0.3 kilometer. So you know why the variation occurs. The 2 to 3 kilometer is during the daytime, so there is a hotter rising, so the height also increasing. So 2 to 3 kilometer is during the daytime, and the night time the air is become cold and denser, so we have the very less boundary layer height, 0.3 kilometer. And so this is the complete troposphere, you can see. Okay, so this is the troposphere. So within the troposphere, so this is the total height. So this is the bound layer height. Okay, and this is the free atmosphere. So due to the surface roughness, that heating and raising of air particle etc. and all, only within this layer is got affected, and this free atmosphere air is not affected. It is a uniform flow. And what happened between these two, there is a capping inversion. Okay, capping inversion means there is a temperature change. So due to that only we can see these kind of flat clouds if you see from some mountain etc. and all. So due to the temperature inversion, the clouds etc. and all cannot climb beyond it. So almost everything will be trapped within this capping inversion layer. So that's how you can see the flat cloud region. Sometime if the cloud has enough momentum, that is the temperature of the air particle is very high compared to the surrounding one, then due to the temperature difference, this will keep on rise due to the very high momentum. So in that case, it will penetrate this capping inversion layer and forms as a very big cloud formation. So which is main reason for the thunderstorm etc. and all. Okay, so complete one is the troposphere, bottom one is the boundary layer which has both mechanical and convective turbulence. Then above that free atmosphere, that is undisturbed flow, and in between there is a capping inversion. Cap inversion means the temperature inversion. So this is just an initial idea. So next you see, so this is the same complete troposphere. In the top we have the free atmosphere. So next we are going to discuss atmospheric boundary layer. So these three are the important thing, the main properties. One is the temperature variation due to the diurnal variation, then turbulence level, how wind profile varies, everything you are going to see. Okay, due to the temperature, how it got affected, then how turbulence varies and how velocity profile varies, you are going to see. And these are all the different layers. So in the image you will see. So this is the troposphere, okay, the complete one. In that, so next to the surface, due to the surface roughness, also due to the heating of surface, that is what happened. Due to the heating, the air particles are rising. When it is rising, it is completely mixed with the surrounding and causing the turbulence. So this kind of turbulence created by this heating of the air particle is called convective turbulence, already discussed. Similarly, due to the surface roughness, mountains, trees, etc. and all, we are getting the turbulence, that is called mechanical turbulence. Due to these two turbulence, and we are getting this layer, boundary layer. Okay, and this boundary layer height, if you see, it varies from maximum 2 to 3 kilometer to minimum 0.2 to 0.3 kilometer. This variation in the height of this boundary layer is due to the day and night. Okay, during the day there will be a more heating, so more number of air particles rising, so the height increases to 2 to 3 kilometer. But in the night, air becomes cold and denser, so it is sinking. So here we are having the very minimum height 0.2 to 0.3 kilometer. Okay, this is how that height varies. Okay, and above one is called free atmosphere, where we are getting the undisturbed air, like a uniform flow, and in between this boundary layer and the free atmosphere, there is a capping inversion. Inversion means mostly they are talking about the temperature inversion. Okay, so in the capping inversion, in the normal neck day also we can see it. For example, if you see from the mountains, you can see the flat cloud formations from the aircraft or somewhere and all. So this is the capping inversion layer. What happened? So due to the temperature difference, the clouds formed etc. and all trapped within this layer, it cannot penetrate further. So most of the clouds are trapped in the bottom layer. So that is called capping inversion. Sometime if the cloud has the enough momentum, that is due to the very high temperature difference between this cloud and that atmosphere, the cloud can further penetrate this capping inversion and it can form a very big cloud. Okay, so here it is penetrated because of the high momentum of this cloud, because the temperature inside this cloud is very high compared to the outside. So due to the temperature difference, this cloud keep on climbing. Okay, so this is about the boundary layer, the lowest layer. Then next to free atmosphere, in between we have the capping inversion. These three are the important parameter in the troposphere. And next, so here same thing. So you see we have the free atmosphere, that is the complete one is the troposphere. So we have free atmosphere, and the bottom one is the boundary layer. In the boundary layer, here they explained due to the temperature variation on the surface how that profile properties are varying. So here you see they mentioned the timing. This is 6 a.m. This is 12 noon. This is 6 p.m. evening. Then again this is night, and again 6 a.m. So what happened? Due to the sunrise, the surface becomes hot, so that the air particles are keeps rising. So this layer also keep on increasing. During the noon, there will be a maximum temperature in the surface. So there will be a maximum convective mixing and maximum layer, maximum height it is reaching the boundary layer. Then the maximum boundary layer height is almost constant up to the sunset condition. Then after the sunset, you see up to this, it is explained here. This is during the sunrise, this is the noon, then this is during the sunset. So this layer they are calling as mixed layer or convective layer. Okay, because due to the heating, the air keep on rises and is mixing with the surrounding air, and there is a convective turbulence. So this is called mixed layer or convective layer. And what happened after 6 p.m. the surface immediately getting cold. Okay, so as the surface temperature dropped, air next to it also got very cold. So as it is cold and denser, it forms the shallow boundary layer. Okay, so due to the drop in surface temperature after the sunset, the air above it cools down, so it is very cold and denser. Due to the denser condition, it sinks down and forms the very shallow boundary layer. So this is called stable boundary layer, or another name is the nocturnal boundary layer. Okay, nocturnal boundary layer. And above that, what happens? Already that mixed boundary layer, this portion is trapped between the stable boundary layer and between the capping inversion. So this is called residual layer. Okay. So here sunrise starts. So temperature also keep increasing. So there is a raising of air particles. It reaches the maximum height at noon and maintains the maximum height up to sunset. After the sunset, surface temperature drops. Okay, so here it is increasing, here it is drops. So air become cool and forms the stable boundary layer. Okay, and that is called nocturnal boundary layer. And in the daytime, this layer is called mixed layer or convective boundary layer. And after the sunset, this mixed layer is trapped within this stable atmospheric boundary layer and this the top capping inversion, that is called residual layer. Again, in the morning sunset, again the air got heated up and it is rising. Like that, it is continuously happening day and night. So here what are the layers we have means convective layer and mixed layer. Then in the night we have the nocturnal boundary layer. Then above that we have the residuals from this convective layer, these three. Then you see there is a surface layer in the bottom. Okay, so this surface layer here also they have mentioned. So these surface layers are due to the surface roughness. Okay, due to the surface roughness, there is a small boundary layer growth on the surface, that is called surface layers. Here they mentioned this as the entrainment zone. In the night they are mentioning this as the capping inversion. Okay, so we have a convective mixed layer, entrainment zone, capping inversion. That all we will discuss in the next slides. Also we have this nocturnal inversion, that is inversion layer generally. So same boundary layer properties due to the different temperature in the day and night they have mentioned, but Whatever we discussed is for the summer. Same thing they mentioned for the winter also. Almost same structure, but it is completely compressed here. Within this it is compressed, because in the winter almost the air become very cold and it is denser. So somewhat similar structure, but it is happening in the that height, boundary layer height alone, it is reducing during the winter. Then here I explained the inversion layer. For example, we have here also we have the nocturnal inversion. Okay, there will be a nocturnal inversion on this stable layer. Also we have the capping inversion. So this inversion means temperature variation, that is temperature inverse increment. For example, in the regular time what will happen, the surface temperature is very high, so it heats up the air, so it becomes, that is, it is rising. When it is rising, then the expanded air parcels getting cooler. So if there is a moisture content, there may be a cloud formation. This is the regular one. Okay, but instead in the night, if you see, okay, night the surface temperature is very cold, so the air next to it is very cold and denser, but above that we have the trapped residual layer. Okay, maybe I will go to that picture. Yeah, here you see. Okay, so this is the nocturnal boundary layer, very low temperature boundary layer profile, but above that we have the residual layer, very high temperature. So because of that, what happens, this cold air cannot go further high. Okay, so now always there is a flow from high temperature to low temperature. We have the low temperature, here we have the high temperature, so the flow cannot go from low temperature to high temperature. So it's stuck between this, trapped between this layer, that is called the nocturnal inversion layer. Okay, so here you can see this is the daytime profile, but night what happened, daytime surface temperature is very high, maybe like a 15 degrees Celsius, etc. and all. So this temperature profile only it follows. But in the night what happens, suddenly the temperature drops, all its the surface drops all its temperature, so suddenly temperature become cold. Okay, then from the cold to, it is trying to reach with the regular original temperature profile, but what happens, here it is cold, here it is hot, so this cool air cannot go to this hot region, so it is trapped and forming the inversion layer. For example, here they have shown during the night what happened, the bottom temperature is dropped, so this here is cool but hot. We have in the top side we have the hot residual layer, and here they have captured like some smoke from the some industries due to the cold and hot, and there's a inversion layer. You see this smoke cannot escape beyond this inversion layer, it is just spread within this inversion layer itself. Okay, so this way we can see in the real time the capping inversions. So this is about the inversion layer, and these are all the two different inversion forms. One is the radiation inversion, another one is the subsidence inversions. So radiation inversion means like in the bottom surface suddenly cool down due to the day and night variation. Maybe during the night temperature is dropped, so this layer is become cool, that is temperature is very less, but above layer we have the residual layer where the temperature is very high, so it cannot cross this layer. Okay, so there is a inversion happening between this. Similarly, if the complete atmospheric air becomes cold and denser, what will happen, that cold dense air try to sinks down. When it is sinking down, it is compressing the layer next to it, so that the temperature, pressure, everything increases in this layer. Okay, this is how the temperature increases and forms the inversion. This is called the subsidence inversion. So here, due to the surface temperature, low temperature, suddenly air got cooled down, so above that hot temperature, so there is inversion. Here the cool air sinking and compressing the layer next to it, so that there is a inversion. So these are the two different inversions. Okay, so we have discussed about the inversion layer in that. Okay, nocturnal inversion, capping inversion. Next we see what is this entrainment zone and this convective boundary layer, how the properties are varying, you can see. So normally in the convective boundary layer, what happens, as I mentioned, the surface temperature increases, so the air particle rises. When it is rises, it expands and cools down. Okay, and if there are moisture content, there will be a cloud formation. So this is how the air expands and cools down in the convective boundary layer due to the surface temperature. And you see how the surface temperature varies for a week. They have mentioned here. For example, so they have mentioned for two different pressure, 85 kilopascal, 97.5 kilopascal. We know pressure will be high near the surface and it keep on reducing. So this high pressure is for the near the ground, and this 85.85 kilopascal is at some altitude. Okay, so near the ground, as you see towards the noon, the temperature keeps increasing. Then after the sunset, again it is dropping to the minimum. Again next day, from the sunrise to noon, temperature increasing. Again it is dropping to the minimum during the night. Like that, there is a increase in temperature and dropping continuously. It is happening. So it is not like each day we will get the same temperature variation. Say during the summer, it is this trend. It is keep on increasing. Okay, the minimum temperature is keep on reducing during the summer, and the altitude also. At a particular altitude also, if you measure, the temperature keeps on increasing during the summer time. So this is how just temperature varies along the surface. It is not like a constant one. So what we discussed, in the convective region, due to the surface temperature, air heated up and raised and expands so that it becomes cool. So because of that, what happens, normally if you see the temperature profile, already we discussed, for the troposphere, surface temperature is very high. As the altitude increases, temperature decreases. This we discussed as a straight line. Okay, this is the close-up view. So surface temperature is around 20 to 15 degrees Celsius. As the height increases within the troposphere, temperature is reduced. Same curve only. Okay, just a close-up view I have shown. And they mentioned the lapse rate, that is, as the altitude increases, what is the decrease in the temperature. So at every 1 kilometer, there is a drop in temperature, that is around 6.4 degrees Celsius drops as the height increases. This is the environmental lapse rate. Okay, so this is called environmental lapse rate, which is around minus 6.5 degrees Celsius. Okay, so this is the temperature profile within the troposphere. But what happened, it is not like a plain single cell. Here we have the atmospheric boundary layer, then we have the free atmosphere. Okay, so due to this atmospheric boundary layer, this this temperature profile varies. You see, this is the troposphere. So we have the convective boundary layer in the bottom, then there is entrainment layer we have, then only we have the free atmosphere. If there is no convective boundary layer, entrainment layer and all, then this dashed line will be the temperature profile where the lapse rate is minus 6.5 degrees Celsius. But now what happened, due to the temperature rise in temperature, the heated air particle rise and cools down, so the temperature is reducing. So instead of following this environmental lapse rate, okay, what happened, the air cools, so temperature drops. It is following this new line, this temperature profile. Okay, so if the convective boundary layer and heating and rising of air particle, then cooling of air particle is not happening, this dashed line alone we will get it. But due to this cooling, this air parcel within this surface is dropped to this way, okay, at the top of the convective boundary layer. But in the free atmosphere, it has to catch up with this line. Okay, so but temperature is dropped here, but in the free atmosphere, temperature is little high. Then there is another layer formed, that is the entrainment layer, which mixes this both convective boundary layer and the free atmospheric boundary layer, so that it balances, equalizes the temperature. This low temperature to high temperature, it is further bringing it. So this is how the temperature profile originally varies because of this atmospheric boundary layer. Okay, so the atmospheric boundary layer is not there it is simply like a single troposphere layer. We will get only one line as a temperature profile. Okay, because of the convective boundary layer and cooling of air parcel, temperature is dropped within this convective boundary layer, but after this boundary layer in the free atmosphere it has to catch up with this temperature, so there is a formation of entrainment layer which do the well mixing and increasing the temperature to the environmental lapse rate. Okay, so the original temperature profile, it will not be a single straight line, it will be like this. Okay, so this is how temperature profile varies, and this is how the entrainment layer is required to balance the temperature difference. Then next is the same. So the green color is the environmental lapse rate, that is minus 6 point, so here I mentioned minus 6.5 degrees Celsius, and in the daytime surface temperature is very hot. Okay, and the air particles rising and cools, so the temperature is dropped. Then there is a entrainment layer, so which do the well mixing, so that the temperature is further again increased to the increased to match with the standard atmosphere. This is for the daytime, but in the night time almost same profile. In the bottom alone surface temperature is dropped, so the surface temperature, that is temperature curve starts from here, then it is increasing, then it is following the same daytime temperature profile. Okay, this how the temperature varies within the convective boundary layer and in the free atmospheric layer. Same thing they mentioned here. So in the daytime what happens, surface temperature is very high. Okay, so and as it is increasing it is dropped, but it has to match with the free atmospheric boundary layer. There is an increase in temperature, so this is called entrainment zone. Okay, that is where temperature is increasing, which is doing well mixing, same way, same profile. Okay, so this is low temperature but atmospheric profile high temperature. Then there is a capping inversion, that is temperature inversion, which is doing well mixing, etc. And only thing is during the night temperature is low at the surface. Okay, this is how temperature profile varies. And here I explained the cloud formation. So we have different types of clouds, so cumulus, cumulonimbus, etc. and all. So mostly we may see this kind of small clouds in the most of the day. Sometime during the thunderstorm, etc., we may see this kind of anvil shape bigger clouds. Okay, two types of clouds we see. So environmental lapse rate already discussed. As the altitude increases, there is a drop in temperature around minus 6.5 degrees Celsius for every kilometer. And there are two types of air. One is the very dry air, another one is the fully saturated, that is wet air. Fully saturated means full of moisture content. Two types of air will be available. Whatever we discussed in the previous slide is for the dry air. Okay, so there is a dry air which is heated up due to the surface temperature, so it expands, that means it cools down. Cools down means it can, as it is very dry, it can it has the maximum capacity to have the moisture content. Okay, as it expands it can hold more moisture content, so that the temperature is further less only, so it is keep on increasing, so temperature is dropped. This is the normal one. Okay, so very fully saturated or wet adiabatic lapse rate means same air, but this time it has the full moisture content. Okay, fully saturated, full of moisture content. So that one, if you heat, what will happen? The fully moisture content air parcel, if it is heated up, it will rise, it will expand and cools. Cools means all the moisture content, it will become, there will be a condensation. Okay, condensation means it will release the latent heat. That means the temperature of this particle is increasing. So here, see, the movement of this air particle is mainly due to the temperature difference. What is the outside temperature? What is the inside temperature? Based on that only it is moving. Okay, that is, the temperature is more, it will keep rising until the temperatures becomes equal to the atmospheric conditions. So here what happened? As it releases the latent heat, the temperature of this air particles keep on increasing, so it's keep on rising above the capping inversion. So this is the temperature profile within the convective boundary layer. Okay, that is for the dry air. So if it is wet, actually here I explained two different wet parcels. Assume here it is 50% moisture saturated, here it is 100% saturated. Okay, so 50% moisture means, so as it rise due to the temperature difference, this moisture content become condensation happens and release the latent heat, so the temperature is always high than the surrounding atmospheric condition. So due to the temperature difference, there is a cloud formation and it is climbing. But what will happen once it is crossing this inversion layer, then there is no temperature difference. So here there is a temperature difference, so it is keep on climbing. When it is crossing the capping inversion or that entrainment zone, there is no temperature difference, so these clouds cannot further climb. It will stay within that capping inversion itself. But if it is fully saturated with 100% moisture content, then you see this is the temperature. This will be for the fully saturated. The temperature difference is more, so it is keep on rising. As it is fully moisture, fully condensation, it releases lot of latent heat. So temperature is always high. It is keep on rising even beyond the capping inversion portion, so that we can see very big cloud formation, etc. and all above the capping inversion. This is how we are seeing some clouds which is trapped within that capping inversion. Some clouds are penetrating above the capping inversion. It is mainly due to the moisture content. Okay, some less moisture content means it will be trapped here. More moisture content means more condensation and more latent heat release. So temperature difference is always there. So it is keep on rising until it matches with the atmospheric condition. Okay. And what is atmospheric stability means? So if there is no there is this kind of big cloud formation and storm formation, then it is atmospheric. Then it is stable. Okay. But if there is a cloud formation, storm formation and all happening, then it is unstable condition. Okay. So these are all the unstable conditions. Previous one. So same thing, same graph for 50%, 100%, just as an image I have shown. So the heated air particle, it is keep on rising. Okay, compared to that, always temperature is high due to the latent heat release. So it is keep on rising at particular altitude. Condensation happens, so there is a cloud formation. But you see here 19, here 19. But after that, there is an inversion layer. That is temperature again start increasing. That is this layer. Once it reaches this layer, you see, from here to here temperature keep on reduces like this, like this. But after that, from 19 to again start increasing. That means this is that capping inversion. So here this is 19, outside 22 or 20 something. So it cannot further climb. So it stopped here. This is for the around some less moisture content. But it has 100% moisture content. Then more latent heat release. You see outside 16 degree, but here 20 degree. So it is further keep rising. Outside 4 degree, inside it is 14 degree. So much temperature difference. So it keeps rising. So here minus 8 degree, here 8 degree. So it keeps rising like that. At particular altitude, the temperature may be both sides is equal. That time it will stop. Okay, like that. We are getting the unstable atmospheric conditions. So we have discussed different layers within the bound layer due to the temperature difference. So we have surface layer, then CBL, that is convective boundary layer. Then in the night we have nocturnal boundary layer and residual layer. Now above that we have the entrainment and capping inversion. Okay, these layers and all you have seen, and how temperature varied within this free atmosphere, that is troposphere, also we have seen, and due to the boundary layer how it varied also we have seen. Okay. And for the dry air how it varied, or for the wet air how it varied also we have discussed. So this is about the atmospheric boundary layer due to the diurnal variation. Next we have same atmospheric boundary layer due to the turbulence level or due to the velocity profile variation, how we are classifying, I have mentioned here. So for example, they have taken the urban boundary layer. So we have around us these many divisions we have, you see. So this is the boundary layer portion. Okay, this is not the free atmosphere, only the boundary layer here I have mentioned. So this is maybe with the free atmosphere. Okay, so above that we have the free atmosphere, below that we have the boundary layer. Okay, the overall it is a troposphere. So we will see only this boundary layer. Okay, we will leave this free atmosphere. It is constant velocity profile, uniform flow with less turbulent. We leave that. Within the boundary layer, how it varies, that only we are discussing here. So if we take that urban, what will happen? Within the boundary layer, we have two regions. One is the outer region or the mixing layer, and inside we have the surface layer. Okay, so within the, that is within the troposphere, we have free atmosphere and we have boundary layer. So this we leave it. Within this boundary layer, based on the wind speed profile now we are discussing, first they are dividing this into mixing layer and surface layer. Okay, mixing layer and surface layer. Then this surface layer, further they are dividing with the inertial sublayer, roughness sublayer. You can see this small rectangular portion they maximized here. So this is the surface layer. Surface layer is further divided into inertial layer and surface, that is roughness sublayer. Okay, inertial sublayer and roughness sublayer. Then this roughness sublayer, further if you zoom, there will be a transition layer, and there will be a, this portion is the urban canopy layer. Okay, so here they mention. So this roughness sublayer divided into transition layer and the urban canopy layer, and this urban canopy layer further divided into two, that is roughness length and zero displacement plane. Okay, so this D is the zero displacement plane. Above that we have the roughness length. So this kind of divisions we have. Same thing I will explain in next slide also. So within that boundary layer we have two divisions, mixing layer and surface layer. The surface layer is further divided into inertial sublayer and roughness sublayer. The roughness sublayer is further dividing into transition and this urban canopy height, and this urban canopy height further divided into zero displacement plane, also this surface roughness line. So these are all the divisions. So first we will see this canopy height and the canopy layer, zero plane displacement, surface length, etc. and all. So here they mention for different terrain. This may be the urban region, this may be the forest, this is the grassland, etc. and all. So within the surface roughness, what we have discussed is the transition layer and urban canopy layer. Okay, so the urban canopy layer means that is the height of the average height of the buildings. Okay, so here you can see. So average canopy height or mean building height. Okay, same thing applies if it is forest, means instead of building we are taking the average, that is mean forest height, or if it is grassland, this will be the mean grass height we are taking, that is called urban canopy layer. Okay, so it then within that urban canopy layer we have two subdivisions. See, one is the Z0, then somewhere here we have the D. So here you can see within the urban canopy layer we have Z0, below that we have the D. So what is this Z0 and D means? See here, if you see the velocity profile within that canopy layer, so it is completely blocked by the buildings, etc. right? So there is no much velocity. Okay, so above the canopy layer only we have the proper velocity profile formation happening. Similarly in the forest also, just a little bit difference is there. So in this branches and leaves, etc. and all, it is completely stopping the flow, so very less velocity. But in the bottom portion, in the trunk space, due to that there will be some air flow, so it is little bit high in that portion. And the grass, if you take, this is also very dense region. So in the bottom and all there is no airflow. Only above that there is a velocity variation starts. So each profile you start, below the canopy region there is no much flow. Okay, above the canopy region only the velocity profile starts. That's what we observed. And what happened? Above that canopy profile, the velocity profile we can theoretically matches with the logarithmic wind profile that we are going to discuss in the next slides. So theoretically, if you match, it will be like a logarithmic profile. And what happens below that? It is difficult to predict, right? What they are doing? So this is the original wind profile, okay, and it is somewhat matches with the approximately matches with the logarithmic wind profile. So theoretically, they are extrapolating this wind velocity profile to the 0 point, that is 0 velocity profile, okay, and that height is called roughness length. Okay, similarly here also above the canopy the blue color line is the original line. So theoretically we are drawing the logarithmic wind profile, extrapolating for the 0 velocity point, then this height is the roughness length. Here similarly here also for the grass, this is the velocity profile. You draw the logarithmic velocity profile theoretically and it will give you 0 velocity point, that is the Z0 roughness length. And what is this D means? In the bottom there is no flow at all, okay, completely it is like completely the velocity profile is shifted above this, okay, that is called zero displacement plane, that is zero plane displacement. Okay, so below that completely there is no much velocity difference and all. So they mentioned the velocity profile itself shifted from here to here, zero displacement. Then extrapolating the wind profile using the logarithmic profile formula, so that you will get the zero velocity point, that is the Z0. So this is D, this is Z0. And how to find the Z0 roughness length means, so this is the velocity profile. Originally they have measured at different location, okay, and this is the normal plot, okay, 0 to 100 it varies, here also 0 to 10 it varies. The same plot if you try it in the semi-log, that is in the y-axis alone, I am taking the log form, that is 0.01 to 100. This log form if you take, this velocity gradient profile becomes a straight line and it will become 0 at one point. That height will give you the roughness length Z0. Okay, same velocity profile. Okay, assume you are using the sensor, you are finding the velocity at different location. For that you are drawing the velocity profile. Okay, and the same graph, if you draw it as a semi-log, it will become a straight line and it will become 0 at some height, and that height will be the Z0 roughness length. But what happens, measuring the velocity at these many points are very difficult. Okay, so normally they will measure just velocity at the 2 points. One is somewhere above 10 meter, somewhere here, okay, then another one is about to that, like that they will take just 2 points, then they will join these 2 points and they will project it to the 0 point. With that they are measuring the Z0. Okay, so if you find all these points also it is possible, but it will take much resource and time. So what they are doing they are taking just measurement at 2 different points. Normally the first point will be at the 10 meter. After that some other point they are measuring. Once you know the velocity, using the similar graph they are drawing the straight line, and where it meets 0 it will be the Z0. Okay, so this is how they are finding the Z0 value for different terrains. So here for example they have mentioned, so overall canopy height for the open sea and the snow and all, there is no canopy height. If there are some obstruction due to the grass, vegetation, building and all, there will be canopy height. If there is no disturbance, it will be a smooth surface, so there is no canopy height. But if you draw the velocity profile, due to the small surface roughness etc and all, there may be a 0.3 mm to 3 mm roughness length, that is the velocity profile if you draw little bit you have to extrapolate, okay, but that is a very negligible height. 3 mm is very small, but if you see the grass etc and all, overall canopy height will be from 5 to 15 centimeter, like a half scale, half feet scale, and that Z0 height is 1 to 3 centimeter. That is, if this is 15 centimeter, this will be just 3 centimeter, like the dimension. Then for the crops, the canopy height is from 1 to 2 meter, and that Z0 will be up to 25 centimeter. Then bushes also almost similar to that. Then urban region, if you take a low-rise building, the urban canopy height is up to 8 meter, and the Z0 roughness length is around 60 centimeter. Then mid-rise building with urban or industrial and all. So urban canopy height is up to 20 meter and Z0 is 2 meter. Then forest and also the tropical region, high forest if you take, it may be from 30 to 45 meter, and Z0 you see from 1.5 to 2.5 meter. And the high-rise building like a city center and all, if you take, the overall canopy may be up to 50 meter, okay, because we have very high buildings etc and all. There the Z0 will be maximum of 4 meter, like that. So they measure different canopy height, okay, that is overall different canopy height, overall height, and what is the Z0, everything they measure.